So let's begin. So we talked about white dwarfs and neutron stars. Now we move on to the third compact object, which is black holes. It's basically a region of space-time where gravity is so strong that nothing, not even light, can escape. And this is one of the predictions of Einstein's general theory of relativity. It has several key properties, one of which is the concept of an event horizon. That's the boundary between the black hole and the universe outside it. We cannot know anything about what's going on inside the event horizon, but we can learn about the universe that is outside the event horizon. That's the radius at which the escape velocity is equal to the speed of light. And inside that, there is a singularity. Okay, of course, this is a theoretical concept because a singularity requires us to have finite mass in zero volume, which means infinite density, which is problematic in various ways. It does not emit anything directly. Okay, there is some very, very weak radiation known as Hawking radiation due to pair particle production very close to the event horizon. However, that is very weak. That cannot be detected with today's technology. But we can detect we can detect the presence of black holes by their effects on the surrounding matter. If there are two black holes that are going around each other, they typically start spiraling closer and closer, and they eventually merge. And in such situations, we are able to detect gravitational waves. And using LIGO, several such black hole mergers have been detected over the last 10 years or so. And then black holes also can produce gravitational lensing. So if you have a stellar mass black hole, which goes in front of a background star, that is going to amplify the flux of that background star. And the star will suddenly brighten up and then fade. So these kind of, this is a strong lensing effect, which has also been observed. So, we detected black holes through gravitational lensing. We've detected them through gravitational waves. And we've also detected them indirectly through their effects on the surrounding matter. For stellar mass black holes, it's not possible to image them directly, but for supermassive black holes, it is also possible to take a photograph of the black hole, and we'll look at that in a few minutes. So there are basically three different classes of black holes. First are the stellar mass black holes, which are typically formed due to the collapse of massive stars. And that 25 is a misnomer, it's a typo. You should probably be around 100 solar masses can form stellar mass black holes. And they have a typical mass of 5 to 50 solar masses. Then there are supermassive black holes. These are also black holes, but they are in terms of their progenitors, they're not formed from stars. These are typically found at the centers of galaxies. And look at the mass range. The mass range is orders of magnitude higher than the masses of stellar mass black holes. And how these exactly formed is not completely certain at the moment, but we believe that they formed fairly early on, and then there were a lot of galaxy mergers which led to the growth of those black holes and so on. Some of them manifest themselves today in the form of active galaxies and so on. So we'll come to that. We'll revisit this supermassive black hole topic again when we talk about active galaxies. Then, of course, there is the concept of intermediate mass black holes. Okay? So how would these be produced? These would typically be produced by mergers of two black holes. Okay? So if there are two black holes, let's say one is a 20 solar mass black hole and another is a 30 solar mass black hole, and the two merge together, you will form approximately a 50 solar mass black hole, right? So 50, 100, 200, then maybe two more merge and so on. So the process can go on. it is not clear at the moment what is the number of such intermediate mass black holes. In fact, there were some people who believed that they shouldn't exist, because getting two black holes close to each other, close enough for them to merge, is not a very easy exercise. Because remember, even if there are two stars in a binary orbit, there have to be two massive stars in a binary orbit. And when one of them blows off and becomes a black hole, the orbit should not be disrupted. The other person or black hole should also be able to coexist. So it's not quite clear what is happening over here. So the evidence is growing. And where is the evidence coming from? It's coming entirely from black hole mergers detected by LIGO. Okay, so LIGO is finding fairly massive 20 solar mass, 30 solar mass kind of black holes that are merging with each other. And the frequency is quite high. So LIGO most people's predictions was that LIGO should not have detected so many black hole mergers, but they are detected. So obviously they're common. So the evidence is growing primarily from LIGO detections. The black hole properties are relatively simple on the gross scale, although the details are very complicated because of general relativistic effects. The Schwarzschild radius, which defines the radius of the event horizon for a non-rotating black hole, is given by this simple expression. Now, you notice here that it's basically just linearly proportional to the mass of the black hole. So in astronomy, it's often useful to remember some kind of scaling relations. Okay, so for example, you should know that Schwarzschild radius scales as linearly with mass. And then if you can remember this constant in some fashion, so the way to remember this constant is that you say that if the sun were to become a black hole, or for a solar mass black hole, the Schwarzschild radius is 3 kilometers. Okay, so now if I say I have a million solar mass black hole, what is its Schwarzschild radius going to be? 3 million kilometers, correct? And if I say it's a billion solar mass black hole, you'll say, okay, it's 3 billion kilometers, and so on. So you can quickly work out that relation and determine it. So I've just pointed this out as an example, but everywhere, whenever you see a relation, try to get the scaling and see if you can normalize it in terms of solar mass, solar luminosity, solar radius, etc. 1 AU, in terms of units that you commonly encounter, then you will be able to intuitively do some back of the envelope calculations to figure out whether something makes sense or not. There is something known as the no-hair theorem, which states that the black hole is a very simple object. It is characterized by these three numbers. It has a mass, it has some angular momentum if it's rotating, and it has an electric charge. And usually this is not very large in most astrophysical contexts. So as far as astronomers are concerned, we talk of two kinds of black holes: a non-rotating black hole, which we call as a Schwarzschild black hole, and a rotating black hole, which we call as a Kerr black hole. So these are the two common kinds of black holes that you will encounter. These, of course, are the names of the early physicists who worked out the mathematics of these black holes.
Does a black hole have electric charge?
How can it have electric charge? It can have electric charge in the sense of if there is some kind of pair particle production near the event horizon, and one of the particles falls inside. Okay, so suppose you form an electron-positron, right? And if for some reason there is a preferential falling in of the electron, then what will happen is you will have a slight charge developing in the black hole. I mean, it's very hard to determine the charge. See, mass is something you can measure. Radius is something you can measure. Even angular momentum is relatively easy to measure. Whereas this is very hard to measure, and it is usually negligible because the probability of the positron going in is equal to the probability of the electron going in. There's no reason to expect that one of them will be preferred to be swallowed. So that's why we say that in astrophysical context, we don't worry about charge. But when you have very small black holes, so you know that there was some story in the newspapers that the LHC is going to produce black holes. Okay, so what are those black holes? Those are like tiny, tiny black holes. Okay, with mass not measured in solar masses, but not even in micrograms. I mean, these are very, very tiny. And for these, the Schwarzschild radius is so small, and the Hawking radiation effects are dominant, that the lot of Hawking radiation happens relative to the mass of the black hole, and therefore you can have situations where the charge is non-negligible in these micro black holes. But in astrophysical contexts, where you have whatever millions, trillions, zillions of kgs worth of black hole, this doesn't happen. So when you do astrophysics, you will basically ignore the electric charge. If they have different charge, they could repel each other. But even before that happens, they evaporate because the Hawking radiation dominates. So that is why people say, don't worry about the LHC black holes. The LHC black holes will last for a fraction of a second because they may be formed, but they will quickly evaporate. They will not start growing and becoming big. Okay, whereas these black holes are immortal. Immortal in the sense that the Hawking radiation is so weak that even if you leave that black hole intact for trillion years, it will just stay there. It's not going anywhere. And they only grow in mass. Our black holes, astrophysical black holes, never lose mass. They only increase them.
What should be the initial mass of object to convert it to micro black hole?
Into a micro black hole, it's not so much mass, but the density. So somehow you have to increase the density to very high levels. See, for example, the Earth. Okay, what will be the Schwarzschild radius of the Earth? Can you tell me? Earth is roughly 1/1,000,000th the mass of the Sun. So 3 kilometers, so 3 into 10 raised to 3 meters divided by 10 raised to 6, so it will be 3 millimeters. So if you can take the whole mass of the Earth and squeeze it to less than 3 millimeters in radius, okay, then Earth will also form a black hole. Right? So it's not so much a question of minimum mass, it's a question of minimum very high density. So if you can, so all of these happens in inside colliders, particle colliders like the Large Hadron Collider. It cannot happen here. I mean, in this room, you can't form black holes.
Black holes can have angular momentum.
If they have angular momentum, they are called Kerr black holes. Yeah, they're two different kinds. They're no longer, it's just a nomenclature. Non-rotating, zero angular momentum, you call Schwarzschild. Okay. Kerr, the mathematical, why do we differentiate between Schwarzschild and Kerr? Because the mathematical equations for Kerr black hole are much more complicated because you have to worry about the rotation. So you're doing everything in a rotating frame of reference. And there is an effect called frame dragging, which comes in general relativity. And that leads to the equations getting quite complicated. So that's why people say, let us take the sort of ideal case. Let's solve the equations for Schwarzschild black hole, which are relatively easy. Kerr black hole equations are very complicated. But in practice, I think at some level, every black hole is going to be a Kerr black hole, not Schwarzschild, because everything has angular momentum. Unless you have some mechanism for taking out the angular momentum, it will rotate at some speed. The event horizon is basically the point of no return. But outside of that, there is something known as a ergosphere. and for rotating black holes. And in this region, space-time itself is dragged. So the space-time, it's a very complicated thing, very hard to imagine intuitively, visually. Okay, but so you have to work out the mathematical equations of that. So you may end up, you have a course on general relativity. Okay, in that course, may end up studying what is the impact of this frame dragging, and that it's possible to do energy extraction. So Penrose has something called the Penrose process, by which you can basically pull out energy from the black hole in small quantities from a rotating black. Around that, there is something known as a photon sphere. It's the orbit of light around the black hole. And further out, there is something known as the accretion disk. So whatever material is falling onto the black hole will have some angular momentum, and it will tend to form a disk of material. We'll look at pictures of this in a minute. And this infalling matter forms a hot, luminous disk. And then, of course, there can be jets. There can be high energy particle outflows, particularly when there is a magnetic field present in that region, which can channelize these charged particles, keep them confined, and allow them to escape at high speeds. Remember, all of this is outside the Schwarzschild black hole. No particle can come out of the black hole itself. Black hole itself doesn't give it anything, but there's a lot of energetic activity that is happening in the region around it. So this is what an accretion disk. So this is your black hole. Okay. This is a fairly inaccurate picture. Okay. Because what happens is when you have a black hole, light is bending. So you may have an accretion disk. I mean, you may have a spherical black hole, and you may have a nice symmetric accretion disk around it, but you will not see it as completely symmetric because light will get bent in crazy ways. So in fact, light that is going from here towards the back side may get bent and come towards us. Okay? So the whole thing will not look symmetric, but that's okay. We're sort of just looking at it, taking out the general relativistic effects. So what will happen is there will be a disk, and through a process known as dynamical friction, as things fall in, they get heated up. Okay? And what is the source of that energy? How is that energy created to heat up the material? Gravitational potential energy. So potential energy is being lost as this material falls towards the black hole, and that is causing it to heat up. Now, because the inner part heats up to very high temperatures, it emits X-rays. Slightly further out, it emits optical rays. Slightly further, UV light. Slightly further out, it will emit optical light. Slightly further out, it will emit infrared light. So because of this, these accretion disks are quite bright at a large range of wavelengths of frequencies. So the same object can be emitting in ultraviolet, it can be emitting strongly in X-ray, it can be emitting in optical, etc.
When radio same accretion disk?
No, the radio emission comes from the jets and from the broadline regions and so on. We'll come to that when we talk about AGN. So everything except radio, or the radio and very long wavelength radio, except for the lowest energy photons, everything is coming from the accretion disk. Okay, so there are several effects that take place in the vicinity of the black hole. Okay, because mass curves space-time and objects always follow geodesics in the curved space-time. Okay. There is an effect known as gravitational time dilation, which becomes quite prominent close to a black hole. So TF is the time in the strong field, and T0 is the time at infinity. Okay. So TF over T0 is given by this expression. So this you can take as the mass of the black hole, and this R you can take as the distance from the black hole center. Huh? We're very far away from the black hole, where the gravitational effect of black hole is not there. So that is what we do. So what will happen as an object comes very close to the black hole event horizon? Huh? Sorry? I'm asking, using this formula, can you tell me what will happen to time when an object comes very close to the black hole? Sorry? Huh. At infinity, the time is not moving. Okay. So the object is falling in, but as you are at infinity, let us say we are at infinity and we are observing some object falling into the black hole. Right? What will we see? As it approaches the black hole, it will appear to become slower and slower and slower. Okay. And see, if you plug in Schwarz, when it comes to the Schwarzschild radius, which is just 2 cm gm over c square, this factor goes to 0, which means infinite time will pass in the distant universe before you see that object falling. So you can never see an object actually entering a black hole because of this. In addition to that, there is something known as the gravitational redshift. Okay? And here again, a similar factor appears. And again here, as like this is the same square root factor here. So this will tend to 0 as you approach the Schwarzschild radius. So the gravitational redshift will tend to infinity, which means what will happen to the light that is coming? If let's say somebody's shining a blue torch from that object falling into the black hole, the blue torch will become red, will become infrared, will become radio, and it will just disappear. So no photons, the photons get so severely redshifted due to the gravitational redshift. So not only are things slowing down, the object is getting so strongly redshifted that you can't see it. So in some sense, even before it reaches the black hole, that object, for all practical purposes, is undetectable by us. We won't see it. Now, this singularity is a point of infinite density according to classical GR. And there are a lot of efforts through quantum gravity type theories to resolve this singularity, because nobody likes a singularity. Nobody wants infinities in the theory. So there are ways in which you can resolve it. Again, this is something we won't go into. So, X-ray binaries. So suppose we saw last time what happens when two stars are circling each other. One is a white dwarf, the other is a regular star. It fills its Roche lobe and causes a type 1a supernova. But before it does that, it can form an X-ray binary. And very powerful X-ray binary, powerful meaning emitting strongly in X-rays, binary stars exist where a black hole is accreting from a companion star. And the strong X-ray emission is coming from the inner parts of that accretion disk. Right? Accretion disk spectrum. Thermal component from disk, power law component from the corona. So why do you get thermal component from the disk? Because just pure thermal emission. X-rays are coming from the hottest part. Optical is coming from the low energy part, and so on. But there can be, just like the sun has a corona, it can have a corona which is heated by the light coming from the accretion disk, and that doesn't follow the Planck function. Okay, it will have its own power law type spectrum. And this can lead to what are called QPOs or quasi-periodic oscillations. So because the accretion may not be very uniform, something will happen, more matter will suddenly fall in, then it'll get heated up quickly. So the object may just flare up, brighten up, few months later it will fade and so on. And Cygnus X1, GRS, these are all X-ray sources, which are accretion, X-ray binaries from within our galaxy. I don't know actually whether but it's non-thermal. So whether it's power law or not, I don't know. But I know it's not a Planck function like the photosphere. Photosphere is a Planck function. Okay. In the corona is a power law definitely in the radio, because that emission is synchrotron emission coming from the corona. But I don't know what is the functional form of the corona spectrum in the optical. Okay. So this kind of thing is also called as a microquasar. And when we talk about quasars later on, when we talk of active galaxies, you'll realize why the parallel is there. So, so it forms this kind of accretion disk. The accretion disk is going to show you thermal emission. However, jets can form, which basically utilize the angular momentum to, so these are like water fountains kind of jets. They'll be symmetric, come out in both directions, perpendicular to the accretion disk, and there will be basically plasma flowing out at very high speeds out of this. And this kind of jets can be easily confined, be very well collimated if there is a magnetic field. And of course, charge particles, relativistic charge particles moving through a magnetic field will radiate. What is that radiation called? You may not know about this, huh? So, suppose you take a non-relativistic charge particle, okay, and you throw it into a magnetic field at some speed. You know, you've done all the Lorentz force and things like that, right? Huh? Sorry? Cyclotron. So that's what a cyclotron is. So that's called cyclotron emission. If the particle is relativistic, then the equations change slightly, and that is called synchrotron emission. So you will get synchrotron emission from these jets. Synchrotron emission is very easy to detect in the radio. So if you look at this object, if you look at it with the X-ray telescope, you'll see strong X-rays coming from the center. If you look at it with the optical telescope, you'll see probably this star, light from this star, and light from the outer regions of the accretion disk. If you look at it with the radio telescope, you'll see the jets or the radiation from the jets. You may not be able to resolve anything because the angular scale of this is very small. So you may not be able to see it like this beautiful picture, but you'll be able to detect the radio waves that are coming from synchrotron radiation that is coming from the jets. Okay, so a bit about gravitational waves. I don't have the time to get into the depths of this, but I think when your course changes next year, I'm sure they'll introduce a whole course on gravitational waves and their detection. So the first direct detection was this object. Typical sources are binary black hole mergers and neutron star black hole mergers. Okay. Any idea why neutron star mergers are harder to detect? That's okay, no? So long as they're merging, we don't worry whether two equal mass objects merge or two unequal mass objects merge. Correct, absolutely right. So, because their masses are systematically lower than the masses of the black holes, and typically the black hole mergers that we are detecting are like 20 solar mass, 30 solar mass kind of black holes. Neutron stars are much less massive. So, the amplitude of the gravitational wave that is created is much less, and therefore it makes it harder to detect. So the neutron star mergers are quite difficult to detect. Even amongst black holes, more massive black holes are easier to detect than less massive ones. Now, gravitational wave telescopes have a property that other telescopes don't have. Okay, which I think I should spend a minute mentioning. Normally, when you want to detect something which is, let us say, twice as far away, right? How much do you have to improve your sensitivity? By what factor should you improve your sensitivity to detect that same object with the same signal to noise in the same amount of time? 4 times. 4 times, because it goes as R square, because you are sensitive to the power that you are receiving, okay, to the intensity. When you do the same for gravitational waves, suppose I have an object which I detect gravitational waves from, and I place that same object twice the distance, how much do I have to improve the sensitivity? Hmm? 1 by R, correct. That's absolutely right. So the sensitivity goes as 1 by R, because remember, we are not measuring intensity, which goes as the square of the amplitude. We are measuring the amplitude itself. Therefore, to detect an object that is twice as far away, you only need to double your sensitivity. You don't have to quadruple it. You can turn this whole thing around and say that, okay, I have I have the ability, my sensitivity allows me to detect, let's say, black hole mergers of a certain mass up to a certain radius. If I double my sensitivity, what will be my event rate? So suppose certain class of black holes merge at a certain rate per unit volume. Okay. Now I have doubled my sensitivity. So how much will my detection rate increase? So for example, suppose I'm detecting from my current sensitivity, I'm detecting 1 merger a year. If I double my sensitivity, how many mergers of the same kind will I detect? 8. Okay, because it goes as the volume. And that is one of the key powers of gravitational wave astronomy, is that once they start getting more and more sensitive, because it's 1 over R versus 1 over R square, it really can beat electromagnetic detectors hands down in terms of their sensitivity. Of course, getting to that sensitivity is a terribly difficult exercise that we will leave for the moment. Okay. So whenever you have a merger happening, first there is a in spiral. So they start coming closer and closer to each other. When they come closer to each other, what begins to happen to the amplitude? It starts increasing. And what happens to the frequency of the gravitational wave? That also increases, correct? So, there's a characteristic pattern that forms of increasing frequency and increasing amplitude. This is known as a chirp in gravitational wave terminology. And once the merger happens, the whole system can vibrate for a while, okay? Because two big massive objects have basically collided onto each other. And then you can get what is called as a ring down signal. And this, of course, by modeling it, the black hole, the gravitational wave signal that you receive, you can measure the masses of the merging objects. With the models, you can even measure the spins of the black holes. And by measuring the amplitude and so on, you can get some rough idea about the distance to the source. because remember the amplitude is going to go as 1 over r, and you can get some rough idea about that. So this has been going on now for a decade. The LIGO has had several observing runs, and they have detected several dozen mergers. Okay, most of them that they have detected are black hole mergers. They have detected exactly one neutron star merger in 2017. Okay, so now coming back to black holes, there is a telescope known as the Event Horizon Telescope. How many of you have heard of it? Yeah. So it basically uses a technique called very long baseline interferometry, or VLBI. Okay. And it obtained in 2019 the first image of a black hole shadow. So in the radio bands, the resolution for a single dish is very poor. But if you take two dishes that are at increasing distances from each other, then the resolution goes on improving as the distance by a factor corresponding to the distance between the two dishes. Now they've used the whole Earth as a single dish effectively, and they were able to photograph this black hole. This is a supermassive black hole, a few million times the mass of the sun. So its Schwarzschild radius is going to be few million, 3 times few million kilometers, correct? So you can see the photon ring, you can see the black hole shadow, you can see the asymmetry due to relativistic beaming and so on. And this can be modeled using general relativity, and it has been done. And this is what you have. So this is, I think, the original image. So this asymmetry is because of general relativistic effects. This is the shadow of the black hole. This is not the Schwarzschild radius, because we know the Schwarzschild radius should be quite small. Okay? But there are two effects here. One, we don't have enough resolution. Things are blurred out because we don't have that kind of sharpness. And also this bending of light is happening in weird ways, and that can brighten up the thing. So this is effectively, that black region is effectively the shadow of the black hole. It's not the black hole itself. The black hole itself is well within, I mean, it's a few million kilometers. It's very, very tiny. But effectively, we have seen the darkening that happens around the region, around the black hole. Because remember, all the effects that we talked of, this gravitational redshift, time dilation, all that is operating within this central region. Okay. Why are black holes important? So if you look at the supermassive black holes, they are quite important in studies of galaxy evolution. They follow what is called as a M sigma relationship. This is a correlation between the mass of the supermassive black hole SMBH and the galaxy bulge velocity dispersion. So the velocity dispersion of the stars in the bulge of the galaxy is correlated with supermassive black holes. And there is a belief in galaxy evolution with lots of evidence now that AGN feedback is regulating star formation. So we'll look at all of these things in detail when we talk about galaxies and galaxy evolution. Then, of course, active galactic nuclei are powered by by accretion onto supermassive black holes. And there's a whole zoo of types: Seyfert galaxies, quasars, blazars, and the like. Again, we will come back to this when we talk of active galaxies. Black holes are good tests of general relativity in the strong field regime. And of course, they're excellent ways. Black hole mergers are excellent ways to study gravitational waves. There's lots of connection to fundamental physics. There's Hawking radiation. There's something known as a information paradox. Okay, because is information being lost? Okay, what happens to the entropy of the universe? Can you decrease the entropy of the universe by throwing all high entropy objects into the black hole? Okay, does that violate the laws of thermodynamics? All of those things. There's a potential link to quantum gravity because gravity doesn't get stronger than it does in a black hole. Maybe there's some quantum effects that come into play, and a purely classical theory like general relativity, maybe it's inadequate to explain everything. So all of these things are interesting. So if you want to learn more about black holes, white dwarfs, and neutron stars, I can recommend this book, Shapiro and Tucholsky. It's a very old textbook, but it has all the details. Everything that we have just skimmed over are gone into great details. So there's a whole like 200-page book, which talks about all of these objects and the physics of all compact objects. Okay, I think I'm going to skip this question. It doesn't belong here. Anyway, so this is the light curve of a supernova known as supernova 1987A. Okay? In our galaxy, for more than 300 years, no supernova has gone off. It is due now. The expectation value is that every 250, 300 years, a supernova should go off in our galaxy, but it hasn't. However, in 1987, a supernova went off in a neighboring galaxy, which is called as the Large Magellanic Cloud. This is supernova 1987A, and this represents its light curve. This was not a type 1 supernova, type 1A supernova. It was a type 2 supernova, basically where there's a big explosion and much of the material of the star was dispersed. There was profuse emission of neutrinos, which were also detected. And what you see here is the Julian date. Okay? So how long do you think it took to fade? Okay. So it became quite bright and then it faded. So it's about from 7,000 to 7,800. So about 800 days, so more than 2.5 years, that thing was detectable. It's fading, 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 fading. So this is, by studying these kind of supernova light curves, one can constrain the models quite well, because every model will say that, okay, as per my model, the curve should look like this. And then you go and observe the curve, and then you see whether it fits the model or not. So now there are more dangerous objects, which are called core collapse supernovae. These are like a subtype of the type 2 supernova. So in very, very massive stars, you can start forming a structure like this. Iron, silicon, oxygen, neon, carbon, helium, hydrogen. And here hydrogen is fusing, here helium is fusing, here carbon is fusing. Except for these guys, iron, that can't fuse anything, can't fuse further. So that can lead to very, very drastic effects. Remember, this can only happen in very massive stars, cannot happen in stars like the sun. Maybe it's nitrogen, I don't know. Maybe it's nitrogen, maybe this is not here. I think I'll check and
what about other elements like beryllium? Are they formed there itself?
See what happens with elements which see this none of these processes are very how does one say, it doesn't go like from element 1 to 2, 2 to 3 kind of. There are complex chains that form. So for example, there is something known as the CNO chain, carbon, nitrogen, oxygen. So carbon goes to nitrogen, nitrogen goes to oxygen, and so on. So the net reaction is more complicated. Even hydrogen to helium process is like we saw the proton-proton chain. It is not as if four hydrogens come together and form helium. No. First, hydrogen has to form deuterium. Deuterium has to form a helium-3 nucleus. Helium-3 nucleus then converts to a helium-4 nucleus. So the energetics of the whole process are such that you can't form all the elements in large quantities, which are the final products. So for example, we don't talk of deuterium fusion because deuterium forms and it gets quickly consumed. So that is why you can have elements missing. It is not as if all 28 elements from hydrogen to helium are there one after the other. It's not like that. That's why you can have missing things. And but it will always be, it should always be in increasing sequence of atomic mass. That much is clear. It cannot, you cannot have silicon above oxygen and so on. Right. So another more extreme example of the core collapse kind of supernova is the pair instability supernova. When the star is very massive, the gamma ray produced in its core can become so energetic that some of their energy is drained away into production of particle and antiparticle pairs. Yeah. This causes a very rapid drop in pressure. There is matter antiparticle pairs are getting created. So the radiation pressure reduces. The resulting drop in pressure causes to collapse under its own gravity. After this violent collapse, runaway thermonuclear reactions ensue and the star explodes, spewing the remains into space. And these are the objects that will not form anything. It won't leave us any remnant. Remember, we said at the beginning, white dwarf, neutron star, black hole, and then no remnant. Pair instability supernova, they form only in very, very massive stars. We'll leave a black hole of about 50 solar. What has LIGO really discovered? It has discovered this. LIGO, of course, can't discover the end product of this because there's no end product. It's just gone. The whole star has just dissipated into space. Okay. So we now leave stars aside. Okay, so we've done stars, we've done the HR diagram, we've done the compact objects that develop from these stars and so on. Now we move on to the interstellar medium, and it's very closely related to the intergalactic medium, as we shall see. And then, of course, we'll talk of galaxies and active galaxies and quasars. Yeah. So what is the ISM? ISM is all the stuff between the stars. What does it include? Gas. Okay. So the gas can be in many different forms. It can be hot and therefore ionized. So ionized hydrogen, right? How can it be detected? Can be detected by H-alpha imaging, because the hot gas will have emission in all the Balmer lines. So you will be able to detect it by looking at it in the H-alpha. H-alpha is the first Balmer line. So at any transition, it's like Lyman alpha. There is H-alpha. Okay. So what transition will it correspond to in the hydrogen atom? 3 to 2, 3 to 2, correct. So it'll 3 to 2. Then you can have at slightly lower temperatures, you can have atomic gas, atomic hydrogen. And this can be well studied using H1 spectroscopy, right? Do you know what kind of telescope you will use for this? H1 spectroscopy. You'll use a radio telescope. because these are hyperfine transitions in the energy levels of the atom. Okay, and it's at 1420 megahertz, so can be studied with radio telescopes. Molecular gas. This is typically formed in dense clouds, right? What do you need to go from atomic? What do you need to do to take some atomic gas and convert it to molecular gas? Huh? Cool it down. Yeah, absolutely. Just like if you want to convert ionized gas to neutral gas, you cool the gas, then it will form neutral gas. Similarly, if you take this atomic gas and you cool it down, you will get molecular gas. And this is typically found in dense clouds inside galaxies and can be detected using sub-millimeter telescopes, because instead of trying to detect the molecular gas directly, which is very difficult, you can detect transitions in the molecular energy levels of carbon monoxide molecules. And there is a scaling relationship between the carbon monoxide molecular density and the hydrogen molecular density. So there are indirect ways using sub-millimeter and millimeter wave telescopes. You can measure the amount of molecular gas in the interstellar medium. What's the second component, big component? Dust. So this is a solid phase component. It's a sort of catch-all thing. When we say dust, no, it is very, very different kinds of substances are present. Silicates are quite common. So these are like sand grains, sand particles. Organic compounds are seen in the interstellar medium. So things like benzene, anything that is not in the gaseous phase. So not methane. Methane you will not call it as dust, but anything that can form solids, can freeze to a solid, so various kinds of organic compounds are found, and metal grains, iron grains, and various other grains. By this definition, even the Earth is a collection of dust, correct? Because we have silicates, we have organic compounds, and we have metal grains. But most of the time, interstellar dust is less than 1 micron in size. So we are a very giant dust particle, the whole Earth. But in the interstellar medium, when you say dust, it means very tiny particles. Then there are cosmic rays. What are cosmic rays? Huh? Particles, what kind of particles? Yeah. Positron, more likely protons and electrons and things like that. Anything that is coming out of the sun in large numbers. So these are charged particles, right? And these are coming from stars. They can also come from AGN and supernovae and things like that. But there is a steady supply of cosmic rays that is coming out of stars. And the last but not the least is the dark matter. And we'll talk more about dark matter when we discuss galaxies. But it's basically likely to be some kind of particles which interact with our regular particles, with the cosmic rays, for example, okay, or with the gas particles, only gravitational. That's the definition of dark matter. The dark matter will not absorb any photon, it won't emit any photon, right? But it will only influence it gravitationally. So if two photons are going, the photons may be lensed by the dark matter. So if photon is passing by the dark matter, it will be lensed by the dark matter, but it will not be absorbed, scattered, or emitted by the dark matter. And this, of course, we'll see influences galaxy kinematics and dynamics. There is no definite boundary to a galaxy, right? There is no such thing as that this is the end of the galaxy. Now the galaxy ends and the intergalactic medium stars. So therefore, most of what happens in the ISM also happens in the intergalactic medium. So the ISM can be thought of as a slightly more dense version of the intergalactic medium. This is the repeated slide. Okay, so if you look at the mass in the ISM, 10% of the total mass is in baryons. All your gas, all your cosmic rays, etc. Rest is dark matter. Rest of the mass is in the form of dark matter. Of the baryons in the Milky Way, about 10% are in the ISM. Where are the remaining 90% baryons? In stars. So the baryon is not a very large fraction of the, ISM is not a very large fraction of the baryonic mass of the Milky Way. This fraction was much larger at earlier epochs. As time went by, more and more gas got converted into stars. And so long as you form low mass stars, once you convert it, it never comes out. Volume of the ISM is quite enormous. It is greater than 99.9999% of the universe in terms of volume. So everything is ISM or IGM. Consequently, its average density is extremely low. Extremely low. So it is in the ISM that we say that, okay, there is 1 particle per meter cube, 17 particles per meter cube, or whatever. Something very, very low number. Part of the ISM? See, dark matter, we don't, it's sort of everywhere. It is not, dark matter is concentrated in halos and things like that. But when we say, no, why are you using dark matter here? Volume means volume, right? So we are actually, you can ding. What is the remaining part over here? Baryons, but the baryons, like gas, for example, is so diffuse that it hardly occupies any volume. So if you take all the atoms in this room, all the molecules in this room, in the air, and you squeeze it down to a solid, the volume they occupy will be negligible. So you do that. That's how you do it, right? So when you count the volume, if there's hydrogen in a place, you say that how much volume is occupied by the hydrogen atom and or the hydrogen molecule, and how much of it is just empty. That's how you calculate the volume. So it is not, so the dark matter may occupy some volume. I don't know whether that was included or not. But this basically, the remaining here is just the volume of stars. Okay. Right. So ISM is not a static thing. It's not as if there is ionized gas which is just sitting there. It is constantly interacting. Okay? So for example, you have some hot gas. It can radiatively cool and form these cold clouds. Within those cold clouds, some kind of condensation can happen and you can form molecular cores. Those molecular cores are the sites for star formation. So stars will form inside the molecular core. And then that will, of course, give rise to stars. Now the stars will start radiating energy, and this feedback from the stars will lead to the heating of the gas. So this is your H alpha emitting gas. So you can have heating. There can also be supernova feedback and evaporation and things like that that can directly take these cold clouds and convert it back into hot gas. So the whole process is very dynamic and very complex. So in general, the star formation process is very, very difficult to model. All the people have tried. The energy content of the interstellar medium. So there is some thermal energy, right? It has a certain temperature. So that will give you the thermal energy of the particles. Then there is a bulk kinetic energy. Okay? The ISM may be in motion. Okay? There are gas clouds which are in orbit around the center of the Milky Way in the disk itself. There are also gas clouds which are outside of the Milky Way, which are infalling or they're spiraling towards the Milky Way. So they'll have some kind of bulk kinetic energy. Then the cosmic rays themselves will have some kind of energy of their own. Magnetic field is ubiquitous. See, we're finding magnetic field in the interstellar medium, we are finding magnetic field in the intergalactic medium, and so on. And so it's very, very weak, of the order of microgauss, okay? But it can still have its own energy. And of course, then the electromagnetic energy, which is all primarily coming from stars, which are emitting radiation. So the ISM is never in thermodynamic equilibrium. It is continuously being injected with free energy, mostly in the form of UV photons from stars and high velocity ejecta from supernovae. So stars are radiating energy into the interstellar medium. The interstellar medium, after it gets heated, naturally it cools. And as it cools, it emits to the extragalactic cold sky. So radiation now leaves the galaxy. We can stop now and continue on Thursday.